Yeah, I think so.
Okay, folks, can you hear me? Wow, there's a big crowd, Peng.
Yeah.
So I'm super excited to introduce Dr. Peng Li. Peng is a friend of many of you in the audience, so he doesn't need a lot of introduction, but Peng's come from China originally. He got his bachelor and master degrees in China from the China University of Geoscience. He did a Ph.D. in my research group. He was supposed to start in 2020, but COVID hit. So he worked remotely for the first year in China, and then he came to Wyoming. In his PhD, he worked on AI, machine learning methods, specifically physics-informed neural network for geophysical exploration. And then he had this amazing opportunity to work as a postdoc at Stanford in a new research group, which is called Mineral X. Mineral X is an interesting research group. It used to be a group working on geostatistics, so statistical modeling of the subsurface for mostly mining and hydrocarbon exploration. I was partially in that research group when I did my PhD, and then a few years ago, they decided to change the objective of the research group and work on critical minerals. They're still doing what we used to call geostatistics, but now it's called AI machine learning. It's exactly the same thing, just with a different name. So Peng is a postdoc there. He's working with Professor Jeff Kers. One of the research directions that they're looking at is decision making. So we build a lot of models. These models are really uncertain, most of all because you cannot trust people like me making models. But because the models are uncertain, when you make a decision, you have to account for the uncertainty in the models. And so there's an entire branch of geostatistics and mathematics and computer science that look at decision making under uncertainty. So this is what Peng is going to talk about. And Peng, I'm really glad that you're here. So the floor is yours.
Okay, thank you, Doris. Yes, I'm really excited to be back here. So today I'm going to talk about the research I did at Stanford. It's about decision making for planning, for geophysical planning, borehole drilling, about critical minerals. So I will start with it's a cartoon. This is made by AI, but I think the situation is very similar. Like, think yourself as a CEO of a big mining companies. You will get a lot of suggestions from your employees, from experts from different domains. Like, okay, let's invest in this money. Let's do the service. Let's drill a borehole. We will win. We will get a lot of money. Some experts might say no, based on my experience or based on my analysis, this model doesn't work. So what should a CEO do? CEO need to make rational decisions, right? They need to make decisions. Every decision matters because every decision means a huge cost. So how to solve these kind of problems? Let me first give us some background about what is critical minerals. Like, right now it's coming out as a thing, but what is a critical minerals? So it's from the Energy Act of 2020. It defines the minerals that essentially to economical national security, and the supply chain is vulnerable and serves as an essential function to manufacture products or economics, something like that. This is defined by USGS. So it's not a static list. So mineral criticality is not static. Why? Because it changes over time, and over time as the supply chain and the market of demand evolves. So if you can see, in 2018, there's only 35 minerals considered as critical minerals. Now it's 60. So it's not a geologic concept or geological category. It's a policy and economic designation. And we can imagine that in the future, this need will increase. So why critical? Like this element became critical? Why? Because of the huge demand from the market. So this is from the analysis by using the market data set. These four elements are essential to battery business, like lithium, nickel, cobalt, and copper. So even we assume that 100% recycling, the gap between supply and demand would be still huge. Like you can see the numbers, like 4 trillion, 3 trillion, 2 trillion, 3 trillion. This is huge. So now we kind of understand, okay, this is the demand is huge. We want more. How to fund it, right? Then we go back to the reality. We think about the exploration pipeline. It's a long pipeline, like from desktop analysis to regional targeting to prospect evaluation to drilling to like development. It takes almost 10 to 15 years from the exploration to production. And it will lead from almost thousands of targets to only a few visible depths. And the success rate is extremely low, normally less than 1%. This is in the ground field. In the brownfield, it might be higher, about 5%, but still low. And if we look at the service, like the investments we want to do that, normally for a geophysical survey, it will involve like 4 stages. From regional scale to the discovery, it will involve multiple data acquisition plans, drillings, geophysical surveys. We will need like this. This is airborne geophysical survey, gravity, magnetic, MT data set. Then we will narrow down the target using ground survey like seismic, TEM, broadband MT. Then we do the inversions. Then we will, okay, it seems there's a high probability that there's just a mine on the ground, then we will do the drilling. Then if you look at the cost, they are expensive. Even for the 4 stages, from stage 1 to stage 4, it will involve hundreds of thousands of dollars to millions of dollars. Even though the success rate is still less than 1%. And if we think about the trend, based on the discovery, it's very hard to find a large ore body right now. Like now, it's the depth of finding a large ore body drops dramatically from like about 200,000 to 200 meters to about 1,000. This is a reality. So this trend means, this is an example about copper. So this trend means we need to deal with deeper, more complex projects that make longer to permit, finance, and construct. So this is a reality of critical mineral exploration. We are dealing with a surge, urgent need from the market, a large demand from market, history low success rate, and a more complex geological models. So the question is, what should we do? How should we deal with this kind of challenge? So my understanding is better models, smart method, and the geoscientists who understand both. So what do you mean like smart method? One of the methods, I think is the right direction, was the planning optimization. So why planning matters, right? Because as we see in the previous slides, we have multi-stages of evaluation, data acquisition from geophysical survey, from borehole drilling, right? This means high cost, but still low success rate. Why? Sometimes the information from that service are limited or redundant without testing before. So if we think this as our motivation, how can we formulate this as a research problem, and how can we do that? So we use this as motivation. We transform this as our research problems. So what we want to solve is that if we have a plan, what will we gain from the plan? This is question number 1. And 2, how can we get the optimal plan? Or if we have 4 stages, what's the optimal sequential plan across different domains? The last one is that we know we can to drill to confirm, to validate the ore body, right? To confirm the height, the grade of the body. So if we know there will be a second plan, should we adjust the first plan or just using the single optimal plan regardless of the second plan? So this is our research problem, and how to do that. I will use an analogy, an easy analogy to understand. Let's say I want to jump. So I want to jump higher, and then we have 3 cases. The base case is that we jump without shoes, and I jump like 0.5 meters. And I go to a shoe store, I tried shoe 1, and I jumped 0.8, right? And then I tried shoe B, and I jump 1 meters. So obviously, right, we can see, oh, we will choose B. This is our plan, right? Why we made this decision? There's some elements we are considering. First one, we have a baseline or base project to compare. Second one, the comparison is between plans and the base project, right? So for choose A, the difference is 0.3 meters. For choose B, the difference is 0.5. So we are comparing from the plan between the base project. And third, there's a metric we are using. Which metric? The meters. We are using the meters as our quantitative metric to evaluate plan A and plan B. So we're going to use this idea to our planning optimization. The question is, what metric do we use? We use a metric from statistics. It's called KL divergence. Basically, it's a concept that measures the difference between different distributions. So the assumption is this. We have a prior uncertainty. The prior model means the existing conditions. Like if we go to a mine, they might have some data like gravity, large-scale gravity, magnetic data, or just nothing. But this condition represents our current belief of the mines. Then we will design a plan to evaluate the plan, the information inside the plan. So we will run inversion based on that plan. Then we will get a posterior. This is another distribution. Then we will compare the base plan, the baseline, and our plan. We will get a metric like this. This will return a scalar, like just 1, 2, 3, 4, something like that. So it makes us to quantify the plans by thinking, okay, this is reduce the uncertainty from prior to the posterior. So our assumption is this. If a plan is informative, meaning that the KL divergence between prior and posterior are large. So if we think about this, it will involve 5 elements. One, we need a model. We need variables we are interested in. We need the ore body. And 2, we need a plan. We can define surveys, borehole drillings, anything we want to test. Then we need the simulations, like evaluations. We simulate this plan by considering every possible scenarios, and it will generate multiple signals. And we evaluate the information inside the signals, and we provide a metric like this. So this is our definition. We call this method the efficacy of information. So this is the definition of EOI. We have a KR divergence like here, and then we simulate the KR divergence in the domain of all possible scenarios here. So basically, it's a KR divergence in all possible D domain. So this is, we evaluate one plan. So how to evaluate a sequence of plans? It will involve the evaluation of a decision tree. So we have a base project like here. We take data A coming here, and then we have some information right here. Do we need to go this branch? So the answer to this question is that we need to compare the information right here, right? Then we need to think this as a whole picture and compare the whole information right here. So this is math. I will not talk too much about that. Then I will give example. This is a porphyry copper 2D example. We use this to generate our synthetic data set. So our target is this area, the alteration area. So this means they have a higher grade about copper. So alteration zone is our target. We want to evaluate the uncertainty reductant given a plan about this. Here we have some existing geophysics service like to provide us some prior, we call it prior beliefs. This is some vague information like, oh, it might look like this, but it contains a lot of uncertainty. So this is how to build our prior models, how to build our prior belief into statistical models. So we have a prior belief like this. We build some objects. The object 1 means intrusion. Object 2 means alteration. The initial model was like this. There's no perturbation right here. We add a perturbation into this, and it looks like this. Then we will use Monte Carlo simulation, generate multiple realizations. It's like 1,000 or 10,000 realizations like this. So these prior models represent our prior knowledge about the prior understanding about the current situation right now. So the question is, what should we do? Should we just go away, or should we conduct a plan, or should we just go ahead and start production? So we will use the method we introduced. Like here, we design a plan. We design, this is a sparse survey. This is an ANT survey, means ambient noise tomography. It's a type of passive seismic data set. So we can design a survey like this. We simulate the signals of survey, put it here like this. Then we do some dimension reduction method to lower the dimension, because geophysics survey are usually high dimensions, and the computational costs are normally very high. Then we use neural network. This is just an AN, it's a basic neural network. But the goal here is to project our data set and our variables, our variable of interest in the same domain. And then here, then we evaluate, we do the inversion. We evaluate all the possible data sets as our observation and do the inversion like this. We do this multiple times, from here, multiple times. We compute the KR divergence, then we compute the UI. So yeah, so this is another common used scenario is borehole drilling. Borehole drilling is another type of data set. Normally, here we use the lithological information from borehole. But lithological information is just a categorical or discrete variables. If we want to use this and project to the same domain, we need to do a transformation and transform this type of data set into a continuous value. So here is the steps. We have a model. We design a borehole path like this. Then we do some transformation and get something like this. Then we use this data set to evaluate the whole thing. Okay, this is the type of data set we assume we want to acquire, right? Then is plans. So how to define the plans? We can define any possible plans we think that's reasonable. Like this, we can define dense plans. We can define sparse plans. We can also define any other irregular plans like that. And then for the borehole, we might consider maybe like for deep one, we think about the boundary of the ore body. Then for deep two, we think, okay, maybe we add some deep angles. Then for deep three, maybe we think, is that okay if we add more deep? So the question is, which one is better, right? And if we know, eventually we will use the borehole drilling. So what sequence would be the optimal one? Like survey to drilling, should we select survey 1 to deep 1, then, or survey 2 to deep 2, or survey 3 to deep 3? Something like that. So this normally can be done by like domain experts. Like normally like a geology expert can tell you, okay, deep 1, deep 2, or deep 3 might be better because they have a larger cross-section. But is there a difference, or is there a quantitative metric to tell us that even we are not a geological experts, we can know, right? So we use our methodology, sequential EOI methodology. We calculate the information behind all of the plans like this. Then we evaluate the combination, the possible combination from survey to borehole drilling. So we will get a metric like this. Yeah, everybody know, right? So here, this is the optimal one because they have a larger metric, right? This one. If you only think about one plan, we will think about this one, right? Straightforward and rational. Then I will give some a case using 3D case. 3D case basically involve more parameters, more uncertainties, and more like we need more complex geological models, right? So this is this is still a synthetic case, but this is from a real case. We extract some important features from here, then we build the prior models. So similar like here. So similar like the 2D case, we need to some variables to define our model, right? So the key is which part is the target of interest. It could be alteration, it could be intrusion, it could be overburden or bedrock. So we have our targets of interest, and then we use this. We consider uncertainty reduction about this target, right? So this is the process of building these prior models. Right here, we will define some object like this. This is just regular geometry. This is just a cubic, ellipsoid, cylinder, cubic. Then we combine all the initial models together. So the next step would be embed the uncertainties. We will use a method called the level set method. Basically, it will add some perturbation to our boundaries and to each of the boundaries, then we combine each object by the geological scenario orders. It will look like this. So this is our prior belief. This is our initial models. It will look like this. So the next step would be, what's the current belief of our targets, right? If we think this as a porphyry copper deposit, our target maybe will be still alteration. Here we are interested in the alteration volume, right? Why? Because this defines the total volume, the economics of this mine, right? Then from prior knowledge, we can have some uncertainty like this. The center would be less uncertain. We know there's something here, but we don't know the exact volume or the boundaries of the ore body. What we want to know is that we try to define some plans and evaluate this and try to provide a quantitative metric for the plan optimizations. Another metric here we involve is that besides the volume, we also want to know the exact locations. Here, right? Here we can define the center as our variables. And then we have some prior uncertainty here. You can see here. You can see that here we define the objectives based on what we want to know. So the objectives are not unique. It's case dependent, based on what you want to know or based on what's your target. But the objectives need to be connected to our prior variables, like we defined previously, like here. So we need to connect the objectives to these prior variables. Then we evaluate the uncertainty reduction. So we have this. The procedure would be same. We design a survey. This is an ANT survey. We use a regular spacing survey. Then we do the simulation. We do the AI predictions. We get the information behind the surveys, like this. Then we will get a scalar number like 0.5. So the design of the survey is case dependent. You can design any survey you want. You think that's possible or that's better, and this method can provide you a quantitative value for this survey. Also, we can define borehole, right? So borehole drilling, we need more variables. We need the XYZ here. We need the deep angle. We need the azimuth angle. Then we can extract the information from the path here. Then next step is evaluation, right? So here we design two type of surveys: ANT survey first, borehole drilling next. We design different patterns about the survey: sparse one, medium one, dense one. We define the borehole based on some current knowledge or geologist perspective. Like here, this is the center, around the center, the boundary of the intrusion and alteration. This is the maximum thickness of the alteration, because alteration is our target, right? This is a borehole with a deep angle. So we can define any possible plans here. Then they run our algorithm. They will provide something like this. We will have a quantitative metric like this. This is our object A, and this is our objective 1. This is our objective 2. And then we evaluate all the possible scenarios here, and then they will project a map here. See? Obvious. If we think this is our objective, the optimal plan would be this one. So dense ANT survey, then followed by deep 3. And here, of course, here we use a technique called Pareto front. We choose this because this is the Pareto front of our whole, multiple objectives. So yeah, so this is basically the techniques behind this model, behind these algorithms. I think the metric we call sequential EOI or EOI provide a metric to evaluate the informations behind the action plans. Know that these plans are not really did. This is only a plan, and we can evaluate the information behind these plans based on the metric of uncertainty reduction or uncertainty minimization. And the second one is, I think the method is pretty versatile. You can use any possible plans you want to do, even for borehole drilling or downhole geophysics, or a large scale or small scale, anything that works. And we can define any possible potential plans. We can even define a plan and run this by the algorithm. It can provide just a metric. And the metric helps us provide information to make decisions. And the information, the decisions are made rational by quantitative metrics. So that's all. Thank you. Yeah.
Okay, so we're going to open it up for Q&A. I will come to you with the microphone, but actually, I'm going to start off with a question of my own. So in one of your first slides, you showed the time frame from like exploration to production being like 10 to 15 years.
Yes.
So my two-part question is, one, how long does it take you to develop your model to potentially bring forth plans of action to industry? And number two, once they have those plans, about how much time would that save in the overall process?
Right. So I would say compared to the 10 years or 15 years of the time schedule, design the plans and evaluate by these AI models are quite like 6 months, like a year. So that's quite short. And the advantage of taking this method is that we can have a quantitative metric to support the decision makers. This is compared to the traditional method because the traditional decisions or the traditional method will use some expert domain knowledge to make the decisions. I think there's two limitations about this. One, it is highly dependent by the experts. Like if we have the best expert in the world, the decisions might be better. Two, it is highly dependent on the data set you have. If you have a good data set, the uncertainty is super low, yeah, you can make better decisions. But in real case, we don't have such perfect data set or such perfect scenarios. Normally, we will have something like, okay, this is, the mine is not obvious, right? The uncertainty is high. We don't know what to do next. Or the decisions are made by high risk scenarios. So I think the advantage of this method is that they can provide a metric or to support the decision makers to make the optimal decisions by just a number. Like everybody knows it. Everybody can directly see that, okay, this is the optimum one. Yeah. Sure.
So first of all, the analogy was great, but I saw you playing basketball. Those jumps are severely over. Said that. So guide me through this decision-making process using the sequential EOI. So you're drilling wells sequentially.
Yeah.
And I guess that you want to measure data in a way that you reduce the uncertainty in your decision-making process when you establish the location of the next well or the number of wells or whatever.
Yeah.
But you are treating it as the there are decisions that you have to make about the data that you acquire as well. And each data set have a different degree of accuracy.
Yes.
So I want to drill a new well. I go cheap. I measure EM data. They're just going to give me a certain value of information in terms of accuracy.
Yes.
I have more money. I measure seismic data. I get a better
Right.
Information about the subsurface. How do you account for that in your the KL divergence?
Yeah. So the question is, if we know some conditions, like if we use large-scale geophysics survey, we get low resolution data sets. If we use dense survey, we get high resolution data sets. How can we account that into the algorithm or the system? So I think that's yes. The answer is yes. This is the case. This is true. But by designing different patterns inside each steps, like if we go to a low resolution survey, we can design different type of service. By designing different type of service, the information they provide are different. What we want to tell or what we want to know is that, can we design an optimal survey, even just by this metric, can we design an optimal survey that can provide maximum information? I think that's one. Two is, we can also evaluate that, for example, here. No, sorry. Here, maybe we don't need a sequential step, because here the survey, the deep 3 or survey 1 already provide a lot of information. So that provides an option that if the increase of choosing a sequential plan is not enough, we can just use this one. If we consider maybe the cost of the operation or something like that, we can think about the optimal single plan, given we already know the outcomes of the sequential plan. So yeah.
So it works really great when you know what to look for. So in a lot
Yeah.
of senses, it's knowledge driven.
Yes.
But a big problem with greenfield exploration is often you don't know what to look for.
Right.
So do you think you could use the neural network to figure out what would be best to look for?
So
Especially provided pre-existing data?
right, I think this is our. Yeah, so this is how can we find the target at the early stage exploration. Actually, my next step, my current project is about this. We try to use, we have some broadband empty data sets, which is very large scale. We want to evaluate, first of all, we need to understand what our current beliefs of the situation. We have data set, what's the information behind the data set about our subsurface models. So we need to do geophysical inversions or analysis or data analysis to understand the current knowledge. So then the problem became, I think became simple or identical or straightforward, is where should we put our next step dense survey? So it would be same as the ANT survey design. We will have a large prior models over there. Then we design different survey at different location or different pattern. They run the simulations and they will return out this metric. So we will use that to say, okay, the next step, maybe dense survey would be better located over there. So I think the methodology would be similar as long as you can evaluate the current delay for your models. Oh, continue.
Hello. So one of the things that is common in industry is to do lookbacks on projects.
Yeah.
Have you taken this method and applied it to successful or even unsuccessful drilling operations and done a comparison of what you would have predicted versus what happened?
So yeah, so in my project, I haven't applied this to a real case study. Right now I'm doing that, but I haven't got the results. But this method, like the decision-making method, are pretty mature for borehole drilling right now, because if you only consider one domain knowledge, like if you only consider one geophysics survey, like MT survey or gravity survey, or if you only consider the borehole drilling, so the scenarios became much simpler. You just run the similar algorithms and design the boreholes. So we already have some successful case about borehole drilling in our group right now. I think it's pretty successful because some startups about this already in California. So yeah.
Peng, thank you for giving us the presentation today and coming back to UW. My question's around, I mean, we all know data in controls the quality of data out. Can you guys not hear me? Or can you hear me okay? Okay.
Yeah.
Can I talk louder? Have you looked at different methodologies with the geological criteria up front to maybe, I don't know, do like principal component analysis or any clustering to try and see if different combinations of your input data sets will inform your output?
This is a very detailed question. So when we do data analysis, actually we did a lot of dimension reduction. You can see here, we use MDS, multi-dimensional scaling. But of course, you can use different dimension reduction methods like PCA or UMath, something like that. Or you can even use machine learning method. To notice that if you want to evaluate a plan, you can use any possible dimension reduction method or inversion method or machine learning method. That's okay. But the key is you need to keep them same for evaluate different plans. So you need to evaluate, you need the exact same method, inversion method, dimension reduction method, and then the metric should be meaningful. Otherwise, if I use a faster or high accuracy method, the metric will be higher. So it's unfair to compare that with different plans. Mm-hmm.
Other questions? No? All right. Well, Peng, thank you so much for coming back. It has been an absolute pleasure.
Yeah.
We have a small token of our appreciation.